Hopefully you see my screen.
Yes, we see your screen. Okay, I think we can.
See, there's New York
there it
City.
is. So
There's New York City, and there's us. It's all woods and lakes up here.
Okay, so yeah, so welcome back, and then we start with the next talk by Erik from Clarkson University, and yeah, please go ahead.
Thank you for having me, and thank you again for thinking of inviting me. This is a terrific group. So I'm going to talk about this paper that just came out. This is the title, Geometric Considerations of Good Dictionary for Koopman of Dynamical Systems. And it's about lots more eigenfunctions than I would have at first guessed, and also about the domain of eigenfunctions. So that's what this picture is from. This picture is from another paper that has some of the background material. So these are the two papers. This is the one that just came out that I'm mostly talking about. And it uses some elements from this older paper of mine with my friends, Chin-Chan Lee, Felix, Dietrich, and Yanis Kevrakaitis, which was about using eigenfunctions for making transformations between dynamical systems. You can actually build the orbit equivalence out of them. So I think for this group, I go quickly through this standard stuff, which is, suppose I have a dynamical system like an ODE. Then I can run and develop orbits as in terms of the semi-flow or the flow, depends on the system. That involves initial conditions. Or an operator version of the story is I can think of a space of functions. And for some of what happens later in this talk, I like L2, but for a lot of other observation functions that will work fine. And then you can ask about what happens downstream on the function. And that's what the Koopman operator does. It says, okay, so I have my point x flows to st of x under the map or the ODE, or I can measure a function g at x, like temperature, and I can measure g downstream at st of x. What this operator does is it says, tell me the temperature downstream, but report it at x, g composed with s of t. This is a version I like a lot of this operator, which is in terms of the push forward, and it's closely related to the pull back operator, which is the Frobenius-Perron operator. They're adjoints of each other. So this should be a familiar story, and that's what I wrote about some time ago with Nartip. So eigenfunctions it turns out that this operator is linear. It's a linear operator. And I think that's gone on about a lot too. But the linear operator, it's the easiest way to guess that is to see it's a kernel form of an integral operator. So being a linear operator, you may guess that, okay, I may have eigenfunctions. And an eigenfunction is a special function, which not only do I measure the function downstream, but when I get there, it looks like the original function, but scaled. So over the phase space, so think of the floor here, this picture is the phase space, and z and an orbit moves, and I can measure a function g at a point at the initial condition, or I can measure it downstream. So an eigenfunction is fitted over the phase space, and I'm going to tell you the value of the function downstream, but I'm going to report it back at the initial state. But it's a specially shaped function so that as I go, I'm increasing or decreasing in a way that scales like an exponential. That's if lambda is real. If lambda is complex, it's oscillatory. So, or I can just think of this as an algebraic statement. The eigenfunctions of an ODE like this follow this PDE. So if the right-hand side of the vector field is F, I'm sorry, this is the wrong F. This has uppercase. This should be the same F. So call that lowercase f. Grad g dot f equals lambda g ends up being the infinitesimal generator of the Koopman eigenfunctions. So you could think of deriving that by chain rule. So how does g change in time? And you get grad g dot z dot, and z dot is f. Or more formally, you derive it by infinitesimal generator, and that's been derived in many places. Like Lesotho Mackie is a great place to look for that. But anyway, let's look at this PD, grad g dot f equals lambda g. So in one dimension, I'm going to work that in a second. In 2 dimensions and up, you need to think about the theory of PDEs. It ends up leading to method of characteristics, and through that you can think about the domain of the function and also the number of eigenfunctions, which is the story I'm driving after. So in 1 dimension, warming up, let's think of this ODE, x dot equals x squared. It's a classic ODE you would present because it presents blow up in finite time. So the solution of it follows by integration by parts. Separation of variables, and it works out to be this. So the flow is 1 over x0 minus t, and you can see that it blows up in finite time as t approaches 1 over x0. This picture is a stream plot picture of the phase space of this guy. So horizontal is t, the vertical is x, and for any initial condition, the solution's increasing, and it blows up at some finite time 1 over x0, the initial condition. So it may not be obvious that it's blowing up in finite time from the picture, but it is. At each initial condition, there's a time where you blow up in finite time. The Koopman eigenfunction PDE is an ODE because it's 1D. So grad g dot f equals lambda g, where f is x squared. So it turns into dg dxx squared equals lambda g. So you can solve this guy by integrating factors because it's in 1D. And you end up getting g equals e to the minus lambda over x. So investigating this function, let's just plot it. This function looks like this. It has a singularity at x equals 0. It's easy to see. And it's a very strong singularity. It's what's called an essential singularity if you're familiar with complex analysis. If you expand it out, you have orders, Laurent series orders 1 over x to the n for all orders n. And it looks very different on the negative side and the positive side, this essential singularity. You can plug it in to the operator just to confirm that if I say e to the minus lambda over x, but I plug in the flow, this guy, into it, and then do some algebra, you do get e to the lambda tg of x because it's an eigenfunction. You can confirm that. The point of this slide is, okay, this guy's easy to work, but the eigenfunction you get out has a distinct domain. So this eigenfunction is only good for either x's in the positive real axis or x's in the negative real axis, but not for the entire domain R. You have to leave out x equals 0. There's another interesting property I want to point out, which is called the algebraic property of eigenfunctions. So based on what we've had so far in the talk, I'm just going to work that in terms of the standard linear ODE at y dot equals y. So y dot equals y, everyone can solve that. It's y of t, the flow is y of t equals e to the t. On the other hand, the infinitesimal generator differential equation, grad g dot f equals lambda g, works out again by integrating factors to be y to the lambda and a constant. So y to the lambda when lambda equals 1 works out to be g of y equals y. And this is often called the state observer eigenfunction. But of course, there's all these other guys for various values of lambda, and you need to be careful. Don't forget, could be a complex eigenfunction, and we might worry about complex eigenvalues. And there's a fun story about that, but I'm not driving up to that right now. Anyway, this guy may seem like the main one or the only one and so forth, and in some sense it is, because there's this beautiful algebraic property of eigenfunctions. And the algebraic property, so this is well known, the algebraic property says if I have, say, 2 different eigenfunctions of the same system, so call it phi lambda 1 and phi lambda 2, I can take multiples of them and the corresponding eigenvalues add in convex combination. And this works as long as I'm in the domain of the functions that you end up building, because when you exponentiate, you can certainly restrict the domain. Think of square roots of -1. So anyway, okay, so this is now the background that I needed. You have this nice algebraic property, and you might think that all the eigenfunctions, all those, let's go at this, all these extra eigenfunctions, they come from just that algebraic property, and that is in some sense true for 1D. But in 2D, the story becomes a bit more interesting. Okay, so just continuing with, I forgot I had this slide. So x dot equals ax, you have a primary eigenfunction x with an eigenvalue a. And you can generate other guys by multiplying them together, like x squared has an eigenvalue 2a from that algebraic property. X times x squared gives me x cubed with an eigenvalue 3a, and so forth. And I can generate all those guys through either the algebraic property or directly by the computation with integrating factors. So that seems nice, and you may think that's all there is, but there's more. So it turns out there's a lot more. So now let's go 2D. So say in 2D, a problem like this, the Koopman eigenfunction PDE, remember grad g dot f equals lambda g, ends up being a PDE of this general form. This is a category of PDEs that you'll find in PDE theory called quasi-linear PDE. And a quasi-linear PDE is nice because it admits something called the method of characteristics. So a PDE generally of this form that is simple functions multiplying the derivatives, the first order derivatives, is called a quasi-linear PDE. So I first learned about this in a classic book in PDEs and in boundary value problems called Fritz John. If you haven't seen this, I recommend it a lot. So the method of characteristics is it's standard material in PDE theory, but it goes like this. You can think of this PDE as being written as a dot product like so, where the A, B, and C are like a vector equals 0, and then the ux, uy, and whatever the thing was on the right is a grad u. And when you say this PDE looks like grad u dot abc equals 0, you're telling me they're orthogonal. So then the grad u must be defining a perpendicular surface. And the perpendicular surface would be perpendicular to a vector field ABC. And so if I want to find solutions, I should write a parameterized ABC equation. So this ends up being what you call the solution, curves of characteristics. So that's kind of the general story behind method of characteristics. So let's go back to the Koopman PDE for a second. So the Koopman PDE was, again, f dot grad minus lambda I phi equals 0. So in other words, this thing. And matching that to the standard form for characteristics, you end up getting, let me minimize this because I can't see what's, oh shoot, I can't see my slides because your faces are there, and I'm in laser, I can't get it to go away. So this is from memory. If I miss a symbol. Anyway, for example, in this example, x dot equals ax and x2 dot equals a2x2. This ends up being the characteristic curves. The point is you get the ODE back plus something that describes the growth or decay in linear terms. So you get this linear term guy here. And I can solve it in closed form. And in this example, you end up getting this expression, which I can't see. So from memory, phi lambda equals x2 to the lambda over a2 and h, because you have this, what I can do is I compose an arbitrary data function on an initial data manifold. And if I state an initial data function h, then those end up at each point X on the data manifold end up being initial conditions along which on the characteristics, which are solutions of the ODE, you propagate the ODE and you substitute back into the PDE. And so this ends up being a general form of the PDE for this guy. So X2 lambda over A2H, and then this ratio. And there's an ambiguity in H, or data H. So that's kind of a main point. This ends up being something a bit more than you would get just from the algebraic property. So that's part of the story. The algebraic property generates lots of extra eigenfunctions, but this ends up generating more than that. There's more eigenfunctions than you would initially guess. So continuing with this example right here, this was the solution we just said, and I can think of it as transverse to the flow. I set a initial data curve, and I can push forward initial H's. What I'd really like to know is what is the eigenfunction at any point X. So at any point X, you can work out through the method of characteristics. What I should do is at the X, I should flow backwards along the flow until I hit the data curve. At the data curve, I'll read off the H, and then I'll tell you the value over here by the push forward. So essentially this says, okay, the eigenfunction is H by I'll call S the position where I pull back X to the data curve. So this right here will be called S star of X. And then R star will be the time it takes me to pull back. And that's what's set in here. So this is a theorem that says those things from my paper. There's a theorem very similar to this in Korda and Mezek, which was they were apparently working on this at almost the same time, but I worked this through method of characteristics. And as such, I have slightly different conditions on the space of functions where this works out. Okay, now the point is there's this H, and H is an arbitrary function. And then I got very interested in counting how many eigenfunctions are there. And are there more or less or same number of eigenfunctions as you would get through the algebraic property? Okay, this is in that paper I told you it just came out like, it's coming out in April. It's like just came out, that paper I cited at the beginning. So again, working with the linear problem because I can do everything in closed form, but I'll drop linear in a minute. This was the set of eigenfunctions. If I plot, a nice way to look at these functions is to look at their level sets. That's a way to visualize it. So here is 3 different sets of level sets for varying the lambda and the A's for each a different H. So this one is H is, I think, 1. This was H is equal to X squared. And this I flipped the role of the A1 and the A2. Anyway, the point is you have transverse level sets. So the transverse level sets you can test out by saying, okay, let's take 2 different sets of level sets. So if this ends up right here, this is one eigenfunction, and this is another eigenfunction that came through from this by choosing different H's. And I can test if the level sets are transverse or not by taking the gradients. So the gradient of one set of level sets and the perpendicular gradient of the other guy. So it works out to be like this for the one level set guy, and then this for the other. And you can confirm that you don't get 0 because they're not perpendicular, but that's what the picture says. But I worked through this computation so that you can kind of see what I'm going to go after in a minute. Now, here's a fact. If I were to take, say, one of these guys, one of these families, and just exponentiate the eigenfunction, like by raising it to powers, like we did with the algebraic property, the set of level sets wouldn't change. So the set of level sets ends up being invariant to exponentiation modulo the fact that sometimes you reduce the domain. So I hope you agree with that. So the fact that I'm getting different sets of level sets that intersect transversely means I'm getting more than you could possibly get just by the algebraic property. There's more eigenfunctions there, and that's because of the ambiguity of, or the data H. So I decided to name something which would be the set of level sets that match, and I call that primary eigenfunctions. I like the phrase Keig for Koopman eigenfunction, which Koopman eigenfunction and eigenvalue for Keig. So let's make a quotient set, which will be the set of all eigenfunctions and their eigenvalues where the set of level sets match, and that's what I mean by this equal with a dot over it. So if I have an eigenfunction and have another eigenfunction and the set of level sets match, then I'll say they're equivalent under this equivalence class, and let's gather all these guys together. The algebraic property of Keigs forms a primary Keig in this phrasing. And that ends up being easy to prove, and that's in the paper. So it's easy to see that this is just a picture of, for example, this problem, x dot equals ax, that when I exponentiate, the levels change, but the set of level sets match. I don't care about how high are the levels, I just care that the set of level sets match. And likewise, these guys from exponentiation. Okay, this is not to be confused, primary eigenfunctions by this definition is not to be confused with this other thing called principal eigenfunctions, which is in Moore, Mezig, and 16. And there's a nice paper about it in 2020 by these folks. That is driving after perhaps matching to what would be the linearized dynamics if I was working in the, I'm sorry, I forgot the name of the theorem that goes with that, the linearized dynamics. Okay, let's work on a bit more complicated problem. So here's a nonlinear ODE that comes from, it's a standard ODE that you would get if you're working the Hopf bifurcation, and this is post-Hopf. I'm going to fix the mu's to equal to 1. So you're basically rotating and heading toward a limit cycle. When lambda equals 1, there's a limit cycle at radius equals 1. It's easier to work to look at it in radial coordinates, but keeping it in Cartesian coordinates. This is what a stream plot looks like. These are beautiful stream plots you get out of Mathematica. So you can sort of see the limit cycle going this way. You can see the limit cycle at r equals 1. So working the problem, the Koopman Pde, f dot grad minus lambda I phi, looking for phi, and then working that theorem I showed you, which says pull back to the data surface, measure the h on the data surface, and then push it forward and scale it. I'm going to state a data surface for h at a fixed radius that'll be bigger than the limit cycle. So this r will be somewhere out here, a big r bigger than 1. So I'm not going to specifically tell you what it is, I'll just leave it in the formula. This ends up working out to be the phi, which comes from that statement, pull back, that was over here, this guy, pull back to the data curve, which is going to be r equal, at a radius bigger than 1, measure the h there, and then push it back forward and keep track of the time it took to get there. And here we are. That's that general form of a Koopman eigenfunction. You can see the lambda in there. You can see the radial coordinates, and most important, you see the h. And this is tan inverse. It's the 4-quadrant version of tan inverse, so we have a unique position. So this is worked in that paper as well. But let's go ahead and investigate this thing. So if I choose h is equal to 1, in other words, the data on that r bigger than 1 surface, h equals 1, this ends up being level sets for that eigenfunction. Here's a picture of that data surface at r larger than 1, because there's the limit cycle. And you notice that the domain of this function, of these functions, are radii bigger than 1, because that's one of the main stories of this kind of discussion. And the set of level sets, I talk about it a lot in the paper, is that you don't typically get one eigenfunction for the whole space. If you have you could think of it as a singularity. The singularity here is the limit cycle. So the linearized dynamics only works in the outer region as long as I can propagate forward in one contiguous section of the flow. That's because of the method of characteristics. But anyway, on this data surface, I set this initial condition, and this ends up being the set of level sets for the eigenfunction. For another guy, this ends up being set of level sets for the eigenfunction. So I can exponentiate this. That's great. Anyway, you see that you may have transverse intersections, as you can see from the picture, but the real way to check that would be through that equation I had showed you before. So when you have transverse intersections, they can't be from the same set of level sets. In other words, they're not from the same primary eigenfunction, Keig. So there's a lot more eigenfunctions than you would have guessed. So that thing I did before.
Excuse me. I think you have to finish soon because you're already over time.
Okay, I can finish in 1.5 slides. So this will be the last story. Is this summary theorem? So this statement I did before, that grad phi dot grad perp another phi, the algebra with that formula I gave you for an eigenfunction works out like this, and you can simplify terms by expanding. And anyway, you can extract a statement like this guy in the end. This one plus this is also in there, and I like this one more. It's a statement, I call it a compatibility statement of H. So this will equal 0 in a very special choice of H and another, to two different H's, to two different data functions. If this is 0, then you may actually be looking at the same functions from the same primary Koopman eigenfunctions. And if not, which is the general scenario that these are not 0, then you'll have different primary eigenfunctions. Okay, I'm going to stop on that. I'll say the rest of the paper I go after. Great. There's these primary eigenfunctions, but can you do something efficiently? It turns out that it gives you a lot of freedom to if I want to represent general data, I can still do it through sums of eigenfunctions in an efficient way. And I develop a whole kind of way of projection and efficiency for that projection. And that was the rest of the discussion, was minimizing things like this, which is a bit PCA-like, but within the set of eigenfunctions. You can see I was ambitious. I didn't get through the whole thing. I never seem to. But we'll stop there. So thank you for having me.
Yeah, thank you very much for the talk. So are there questions?
I'm going to go back to the papers at least so you can look at that.
I think Jochen has a question.
Yes.
But I think somebody else was first, Alexander Romanov, maybe?
I also had a question.
I was just clapping.
Sorry, maybe I didn't get this, but what was the relation between your primal eigenfunctions and I think Matthew Qualheim calls them principal eigenfunctions? Do they coincide?
No, they don't coincide. So the principal eigenfunctions seem to be after describing the linearized dynamics. So if you have let's say you have a fixed point and you linearize the dynamics through, and I'm just drawing a blank. Whose theorem is the traditional in ODEs?
Do you mean Hartmann-Grobman? Yeah.
Yes, Hartmann-Grobman. I slipped my mind. Through Hartmann-Grobman, then in a small neighborhood, the dynamics is diffeomorphic to the linearized dynamics. And the principal eigenfunctions are after extracting the eigenfunction that corresponds to this, and there's a bit more to it. The primary eigenfunctions is a different thing. It's about a quotient set of eigenfunctions, because there's more than just that primary eigenfunction, which is what my discussion was about. So since there's so many eigenfunctions, I thought, well, maybe the whole story is just about exponentiation, that algebraic property, but I ended up saying, no, there's a lot more than that. And the primary eigenfunctions was a way of really categorizing them. So it's a quotient topology over all those eigenfunctions that have matched level sets. And it's not just the primaries.
Okay, and would you say that maybe those principal eigenfunctions are then some special representants of those?
Yes, I would definitely say they're special because they're the ones that will match like the linearized dynamics that maybe propagate. You can think of it as propagating by method of characteristics through my language from a neighborhood near a fixed point where you did the linearization. These principles, I just flip my words, these primary guys can be special in their own way, because there's a computation about efficiency that I get into later in the paper, the long version of the talk. So they're both special in their own way, but primary is definitely special.
Okay, thank you very much.